Hi, this is Roger from Kanka Labs, and now in the second part of the series about True-RMS measurement, we'll take a look at some other things that are important about the accuracy that you can expect when measuring AC voltages. First part, we discussed what a big difference it makes if your multimeter has true RMS AC or true RMS AC plus DC measuring capability. Now, let's see what other factors are important. I've taken the data sheet of one of the standard true RMS to DC converters, which is the analog devices 8736 that is used in many multimeters. It is available for now around 30 years and still one of the standard ICs for RMS to DC conversion. Now, it has a base accuracy of 0.3% or otherwise 0.3 millivolts in the inputs. And it is already set in the introduction that there are two factors you have to take into account. The first is the frequency range, which we take a closer look at in a minute, and the second is the so-called Crest factor, which I'll explain in the end. Now let's first take a look at the frequency response. And there's one thing you should know about the frequency response in most true RMS to DC converters. The frequency response is not constant with amplitude, but the lower the amplitude you measure at the input of your converter IC, this is not the input of your multimeter, but the input after the input attenuator of your multimeter, the frequency response drops, and in the lower measurement ranges around 1 millivolt, it drops for this IC even down to a few kilohertz. So this is something we will try to verify later when measuring true voltages with 3 different multimeters, if we really can see this effect. And the data sheet also has some figures about the frequency range. Here we can see 1% additional error, and this should be the limit for accurate measurements, is already reached at 1 kilohertz when you only measure 1 millivolts RMS. If you go to the higher levels, then you can measure up to 90 kilohertz. And let's compare this to the specs of my X-Tech Multimaster 570A. Here we can see in the lower frequency ranges, the accuracy looks suspiciously near to what the 8736 gives, 0.3%. And up to 5 kilohertz, there's still no drop in the at least in the range up to 500 millivolts, and it starts to get worse only above 20 kilohertz. There from 20 kilohertz, which you can see here, from 20 kilohertz to 100 kilohertz, the accuracy drops to 2.5%, which is for this frequency range and a mid-range multimeter still acceptable, but you should know about this factor. Now, in comparison, the cheap Uni-T UT139C, which we have here at the lab as a cheap multimeter for all-purpose measurements, it has an accuracy around 1%. And it gives as a frequency range only up to 1 kilohertz. So we'll also check this later with true signals, where we compare the two RMS multimeters with the third one, the averaging multimeter, that I already showed you in the first part of the series. Now, there's still, except for the frequency range of the converter IC, there's still something else you have to know. Every multimeter has or every usual multi-purpose multimeter has an input attenuator at the input. We'll draw a very simple one with only one tap. And let's suppose we have here 1 meg ohm of input resistance on the lower side of the voltage divider, and we have 9 meg ohms on the upper side of the voltage divider. Now, if we tap off the voltage here, which goes to the RMS converter IC, then of course, when this is the input, the measurement input, then of course we have a division ratio of 1 to 10. So at this point we get 1/10 of the voltage of the input. So that's no problem at all, but you of course always have parasitic capacitance. And let's presume we would have a parasitic capacitance of 30 picofarad. Now, there's a little problem because this forms a low-pass filter here, and if you put in the numbers for the limiting frequency of a low-pass filter and you take 1 meg ohm and 30 picofarad, then you get a limiting frequency of only around 5 kilohertz. So what use does it make when your True-RMS to DC converter IC has a frequency range perhaps up to 90 kilohertz in the higher voltage levels? But if you neglect the input capacitance, the stray capacitance of your input voltage divider, then you lose all the frequency range of your good converter IC. Of course, there is a remedy for this, and you know this perhaps from your oscilloscope. If you put on the stepped attenuator a second, on each resistor, a fitting capacitor in purpose, which in this case would be 3.3 picofarad. Now, if you put in the numbers, you get a resistive voltage divider, and you get at the same time a capacitive voltage divider, and then you get away with the low-pass filter effect, because for every in an ideal situation, if they are closely matched, the resistors and the capacitors, which are often trimmable, at least the lower ones, if you closely match them in the same ratio as your resistor divider, then you don't have any low-pass filter anymore, because the division ratio is now equal for every frequency. And I believe, or I imagine, that that's exactly what they neglected here at the cheap Uni-T. If it goes only up to 1 kilohertz with its 1% accuracy, then you can suspect they simply didn't put a capacitive voltage divider on the input divider stage. So, of course, it's not an RMC, but an RMS converter. So that what you have to know about the frequency range when you measure AC voltages with a True-RMS multimeter. And now let's take a look at what it's about, the Crest factor. So you can of course look up at Wikipedia what's the definition of the crest factor, but as the old saying says, a picture says more than 1,000 words. Let's just take a simple example with a sine wave. And let's suppose we have an effective or RMS voltage of 100 volts. Then we know that the peak value is the square root of 2, which is around 1.41 and so on, times the RMS or effective value. So we get a peak value of around 141 volts. And now the crest factor simply is the ratio of the peak voltage divided by the RMS or effective value, and in this case it's simply square root of 2 or around 1.41. So that's what the crest factor is. So now let's take a look at some examples for the crest factor that you also can find, or which I've copied or printed out from Wikipedia. For a sine wave, we've just seen that the crest factor of a sine wave is the square root of 2 or around 1.414. For a more, let's say, complicated waveform, which is of course technically not a very exact term, let's see a half-wave rectified sine wave. The crest factor already becomes larger. It's here 2 in this case. And with real signals that you usually have to deal with in your measurement praxis, the signal that you most often have to do with where the crest factor comes into play are PWM signals. And there the crest factor is simply the square root of the period of the PWM signal divided by the on time. And you can easily see if you have, let's say, a ratio of period to on time of 10, it's the square root of 10, which is around 3 point something. Now let's take a look at what the data sheet says about the crest factor. And we again take as an example the 8736 from Analog Devices. And we can see as long as the crest factor remains below 3, then the additional error for, let's say, distorted or more complicated signals than a sine wave is only around 0.7%, which is of course acceptable. But when the crest factor becomes higher, and that is especially true for PWM signals with a very high ratio of period time to on time, then the additional error even gets in the 2.5% range, and you should at least know about this. And there is of course another factor. We know now that that we have a frequency limit for a certain accuracy, and you probably know that any signal that is more complicated, let me use this term here, than a sine signal, consists of a fundamental harmonics, which is the sine wave or the frequency of the base frequency. And then there are additional harmonics, multiples of the base frequency, and a signal like this, a PWM signal, has an infinite number of higher harmonics. And now even if your multimeter can measure relatively accurately with a crest factor, let's say up to 3, but you have to watch out. The higher harmonics of these PWM signals are perhaps already outside the frequency limit of your true RMS circuitry. So there will be not only an error due to the crest factor, but there will also be an error due to the higher harmonics in the signal, which your true RMS circuitry cannot measure anymore. So let's suppose you're measuring a 100 kilohertz signal here with a 100 millivolt input level, and we see that we get to around 200 or 300 kilohertz, let's say 200 kilohertz, and then the sensitivity drops off. And now suppose you're measuring a rectangle or PWM signal where the first harmonic is the third harmonic, which is the three times the base frequency. Now this would be already outside the range where you get more than 1% error, and that is independent, or better say this comes additionally to the error induced to the crest factor. So there are at least these 2 points, the frequency range of your multimeter and of your true RMS input circuitry, the dependency of your frequency range on the input signal, and additionally the crest factor of your signal. So you should be very careful when interpreting either high frequency signals or signals with a crest factor higher than 3, or don't expect too much accuracy from your multimeter. And we'll compare now these behavior with our 2 or 3 multimeters that we already had for a comparison in the first part of this series. So, to be fair, we start our comparison of the frequency range of the different multimeters with a 100 Hertz sine signal from our analog frequency generator or function generator, and our Rigol DS1054Z gives us an RMS value of 1.95 volts, and this is all of the 3 multimeters are within range. Most trustworthy is of course the X-Tech because it has the best specifications, but now even the Uni-T at this low frequency and pure sine signal is within its 1% accuracy, and even the cheap averaging multimeter is with 1.95, also within about 1% accuracy. Now let's crank up the frequency and see what happens. We'll go in steps of 10. So the next step is 1 kilohertz, and the Uni-T still with the sine signal is within range, within 1% accuracy. Now the averaging multimeter already starts to drop. Let's see what we get when we crank up, when we get to a higher sensitivity of 2 volts full scale. Well, then it's again within range. Perhaps this is already a sign that the input attenuator of the cheap multimeter is not frequency compensated, because the displayed value at 20 volts, which is only now about 1/10 full scale, is lower than when we go to the 2 volt range. So now let's go again up to a factor of 10 in frequency, and we are now at around 10 kilohertz. And now the strange things happen with the cheap averaging multimeter. the value now has even become greater than 2 volts, and that is also a sign of a non-compensated input attenuator, because apparently there seems to be a kind of a resonance. So at frequency of higher than 1 kilohertz, there's really no more use in this cheap averaging multimeter. And astonishingly, the Uni-T now displays 0, 0, 0, 0, which means it cannot display any frequencies much higher than 1 kilohertz. So that's a clear indication of its limited bandwidth, while the X-Tech still is within 1% of the range of the value that the RMS value that the Rigol has calculated from the waveform. And now let's go again up a factor of 10 up to 100 kilohertz. And the X-Tech still is now not anymore within 1% of the value the Rigol displays, but we cannot accurately say which one is more correct, because now the X-Tech gets near to its limiting bandwidth, and the Rigol is specified only for an accuracy of around 5% in the displayed values. So still a very good result. And now let's go to 1 megahertz and see what happens then. And the X-Tech still is displaying a value, but now it should be 1.93 volts RMS, and we are only getting 1.56 volt. Let's see, we are in the True-RMS AC plus DC mode. Let's see if this changes if we go to only volts AC. No, we get the same value. This is the DC, AC coupled measurement, which is the same as with the Uni-T, which is also only AC coupled. You can see it perhaps at the symbol of the sine wave. And if we go back to AC plus DC measurement, you can see a double symbol with the sine wave, and above it there is an interrupted DC symbol. So apparently 1 megahertz is out of the frequency or usable frequency range. So now let's investigate if the frequency range of especially the X-Tech, which is the highest quality one, if it is dependent on the signal amplitude. Therefore, I've gone to its limiting frequency of 100 kilohertz and gone to the upper range of the millivolt range, which goes up to 500 millivolt, and now I'm feeding 458 millivolts RMS sine input into it. And now let's diminish the amplitude. Of course, the other two are completely useless here and give totally wrong results, as we've already seen, due to the high frequency. And now let's turn down the amplitude in factors of, or in steps of 10. We go down to now around 47 millivolts, and it's still within range. We cannot say if the difference to the calculated value from the Rigol DSO is according to errors in the Rigol or in the X-Tech, but I would say still within 1% accuracy. Now down to around 5 millivolts. Of course, the signal shape here becomes worse. We get around 5 point something millivolts RMS from the Rigol, and now the X-Tech has gone totally out of range with 60-70% error. It only displays less than 2 millivolts. So that's exactly the effect we saw on the datasheet of the analog devices True-RMS to DC converter, that the frequency range or the bandwidth drops if there are very low signals fed into the True-RMS converter. So it's clearly visible, though it only becomes apparent at very low amplitude and at the highest frequency that the X-Tech still can measure. But you should know about this effect, that when measuring at the limit of the bandwidth and with very low signal amplitudes, then the bandwidth becomes smaller, or the limiting frequency drops. So just a proof to the theory or to the data sheet what a classical or typical true RMS to DC converter circuit will behave like with high frequency and low amplitude signals. So, and finally, let's take a look at the influence of the Crest factor, which we explained at the beginning of the video. We start with 100 Hertz to give the Uni-T a fair chance, so that the harmonics of the signal that we just will be changing in a second aren't outside its frequency range, so that we have no error due to harmonics that are suppressed by the limited bandwidth of the Uni-T. So when we have a 100 Hertz sine wave, even the 10th or whatever wave, even the 10th harmonic will at 1 kilohertz will be within the bandwidth of the Uni-T. And again, we start with the sine wave, and all three give reasonably well, are all display nearly the same value. 136 millivolts is of course the most correct ones, but we see now the Uni-T still again is quite well inside the 1% accuracy. And now first of all we change to a square wave, which we have seen has a crest factor of 2 compared to a sine wave which has a crest factor of 1.4. Now the Uni-T drops again in accuracy. The correct value is again on the X-Tech with 202 millivolts, and we are here, okay, it's less than 1% out of the value of the X-Tech, but still noticeable. And now we change the duty cycle of the square wave. The reason why the square wave doesn't look very good is because I have in parallel at the 50 ohms output the Rigol DSO and all of the three multimeters, which of course present a non-50 ohms load. So that's where the distortion comes from. And we go to a square wave with a duty cycle of around 15%. This should give us a crest factor around 3, and still the Uni-T is within 1% of the X-Tech, so that's quite okay. And according to the data sheet of, for example, the analog devices 8636 or 736, a crest factor of 3 still should not present any problem to the RMS to DC converter circuit. But now if we go up with the frequency from 100 Hertz only to 1 kilohertz, the displayed or calculated value from in the Uni-T significantly drops. It's now, well, 15 units, which is around 10% too low. And in this time, this is not because it cannot measure signals with a crest factor of 3, but the reason is that the higher harmonics of this PWM signal are outside the limiting frequency range of the Uni-T. So when measuring signals that are non-sinusoidal at the bandwidth limit of your multimeter, oh, the auto power off has fooled me again. Let's turn it on again. Go to AC mode. So if you are measuring non-sinusoidal frequency at or near the bandwidth limit of your multimeter in True-RMS AC mode, then you cannot trust the value anymore simply because the harmonics are outside the frequency range. The X-Tech still has no problem with this signal, even if we would go again a factor of 10 in frequency upwards. We are now at 176 millivolts, which is well within what the Rigel displays us, and the Uni-T has again nearly dropped to 0. It's only displaying 1.7677 millivolts, which is only 1% of the true value. So that should make you aware of where the limits of your multimeter are, and again, you get what you pay for. If you have a high bandwidth True-RMS AC+DC multimeter, it will give you much more reliable results at signals with higher frequency than the cheaper ones, and signals at high frequency also with a crest factor of up to 4 or 4, 5 or even higher. So I hope you liked it. Perhaps you could learn a little bit about multimeter specifications, and hope to see you next time when you can await a further episode in this series, and this time it will be about True-RMS power measurement. Here we only have measured the RMS voltage, but when you want to measure power, you have to take into account voltage and current, and how this is done will be the content of the next episode. So that was it. Bye from Kanka Labs, bye from Roger, until next time.